And now for the thrilling conclusion to work and energy. So, previously we mentioned that work was, that's not what I'm looking for. That's what I'm looking for. Is F delta D cosine theta. Work is equal to force times distance times the angle of between the two, so that we're looking at the force in the direction of the displacement. Today we're going to talk about energy, which is defined as the ability to do work or cause change. So right off the bat, we see that there is this tie-in, this connection between work and energy. Like work, energy is a scalar quantity, which means that it doesn't have a direction. It's just our magnitude and unit. And it comes in many, many forms. Our two broad forms of energy are kinetic, which we probably learned at some point is the energy of motion. So anytime something is moving, it has kinetic energy. And then the other is what we call potential energy, or stored energy, and it's typically stored due to the object's position in some type of field of force, whether that's gravitational or electrostatic. But it's energy that is there ready to use, that has the potential to be used. So we look at a couple more specifically. The probably most common one that we experience on a daily basis is the gravitational potential. And the gravitational potential energy of an object is based on that object's position in a gravitational field, as well as the mass of the object. Now, for our purposes, we're going to be focusing on the change in an object's gravitational potential, which depends on the change in its height over or within a given gravitational field. So our equation, mathematically, U is our symbol for potential energy. So U is our general symbol for potential energy. And we have our subscript G for gravitational potential is equal to the mass times our gravitational field strength times the change in position within that gravitational field. And so a couple things to recognize here. And one thing to actually notice, maybe we'll notice that this equation right here, or this portion of the equation, is the same way that we calculate the force of gravity. But again, this G is planet specific or gravitational field specific. So for Earth, the gravitational field strength is 9.8, but for something like the Moon or Jupiter or Mars or Neptune, it's going to be something very different. And then this delta Y is the change in height or the change in vertical position. Okay. With this, the change in position is important because we're really focusing on the change in energy. And again, this kind of ties back to our discussions on frames of reference and setting specific frames of reference. I can do the same thing with my gravitational potential. If I say that this is my zero gravitational potential energy position, then if I raise it up, I'm going to add or have a positive gravitational potential energy. And if I lower it down, so let's say it went down to the floor, here I would be taking away gravitational potential, and on the floor it would have a negative gravitational potential energy because it's all based around this frame of reference on the table. If instead I set my zero position as here, 0, gravitational potential, and then I were to raise it up to this height, to table height, I would have some positive gravitational potential, excuse me, and if I were to raise it up to this same height, I would have some positive, twice as much gravitational potential. But what it's important to understand is that the change in gravitational potential energy for both of these is going to be exactly the same. If I go up, it's going to be a positive delta UG. If I go down, it's going to be a negative delta UG. And the magnitude of that change is going to be the same regardless of what my frame of reference is. Then we have elastic potential energy. And elastic potential energy is energy that's stored in a spring or some type of elastic material when we compress it or stretch it. And our equation, and actually, so we should have US, there should be an S there. US is equal to 1/2 kx squared. And K, just like with our previous equations, K is our spring constant, and you'll hopefully recall that force is equal to negative Kx. This is our Hooke's law relationship. And we found this when we looked at the relationship between force and displacement, and we saw that that was a linear relationship where the slope gave us the K value. And so when we stretch springs or elastic bands, or we compress them, we're storing energy in that compressed or stretched material. Then we have kinetic. And our kind of macroscopic kinetic energy, the equation for that is 1/2 mv squared, where K here is our kinetic energy, m is the mass, and v, of course, is the velocity. And notice that the variables that affect the kinetic energy are the exact same two variables that affected the momentum of an object, the mass and the velocity. But the tie-in between those two is slightly different. We had momentum was equal to just mass times velocity. Kinetic energy is equal to 1/2 mv squared. So one thing to notice then is that the velocity actually has a more significant impact on the kinetic energy of an object than the mass does. And then within this, we have other types of kinetic energy that we can talk about, and we will talk about over the year. Thermal energy, which is the energy of motion of atoms and molecules. Electrical energy, which is the movement of particles or electrons, charged particles, through objects or through conducting materials. We have sound energy. So those are all some specific examples of kinetic energy that we'll address. Now, at our macroscopic levels, we use this term mechanical energy to talk about the total gravitational and kinetic energy in a system. And we do this because these two types of energy are very easily converted. And actually, we're going to add in a lot of times elastic potential energy into this because these energies are common and they convert very easily from one to another, and it helps us to solve problems as well. And so within this term, or with this term of mechanical energy, it's easy to talk about all of those kind of wrapped in together. Now, if we talk about our units for energy for a moment, we have our three equations that we already provided. Kinetic energy is 1/2 mv squared. Gravitational potential is mg delta h. And elastic kinetic is 1/2 kx squared. Let's take a look at our units for each of these. So kinetic energy, the 1/2 doesn't matter. Mass is kilograms. We have meters per second times meters per second. So that gives us kilograms meters squared over seconds squared. Over here for our gravitational potential, we have mass in kilograms. We have the gravitational field strength, which is newtons per kilogram, but I'm going to simplify that to meters per second squared. And then our change in y position or change in height is meters. So that simplifies to or combines to kilograms times meters squared per second squared. And then our elastic potential is 1/2 kx squared. Again, 1/2 is dimensionless. So we have k, which is newtons per meter, x squared, which is meters squared. So we have kilograms. So this actually cancels out here. This cancels out here. We can expand kilograms, or newtons rather, to kilograms times meters per second squared times meters. And so our units for elastic potential are kilograms times meters squared per second squared. So what you'll notice is that our units for all three are the exact same, kilograms times meters squared per second squared. That's a good thing because they're all measures of energy. And regardless of the form that energy takes, it should have the same units. Now we combine these, much like the kilogram meter per second squared is the Newton, the kilogram meter squared per second squared is called a joule, named after English physicist James Joule. James Joule. Now, the other thing that you might recall and notice is that this is the same units as work. What? I know, it's ridiculous. It's crazy. But it's also amazing. Because physics. Now, in our previous set of slides, we said that the work was defined as the force applied over a distance, or a force acting over some distance. A probably better definition of work, or more useful definition of work, is the change in the energy of an object or system. So work done on a system is equal to the change in energy, say delta E, of the system. Now, when viewed in that light, it makes sense that the work and the energy should have the same units. Work is the change in energy, just like the change in any value has to have the same units as that value. If you're talking about the change in temperature from 70 degrees Celsius to 100 degrees Celsius, the change is 30 degrees Celsius, same units. So it's a good thing that they have the same units. Now, when work is done on that system, we either add energy in or we take energy out. So we mentioned before that work can be positive or negative. If we do positive work on a system, we're adding energy into the system. If we're doing negative work on the system, we're taking energy out of the system. For one that has only mechanical energy, work changes the potential and or kinetic energy in the system. And really, this kind of ties back in, and we'll get to it here in a second, the idea of open and closed systems, internal and external forces. If the work is done by internal forces, the total energy of the system stays the same, and we're simply converting between the types of energy within that system. An easy example is dropping a ball in a gravitational field. You're doing work on the system, you're converting potential energy to kinetic energy, but the total energy of the system remains the same. Okay? So this kind of leads us to the idea of conservation of energy. And in a closed system, and again, same ideas as we talked about with momentum. Closed systems versus open systems. External forces versus internal forces. In a closed system, the total energy of the system doesn't change. The most typical or the most common way that we have energy within a system change, though, that most common external force is friction. And it could be fluid friction, so like air resistance, or it could be regular old friction between two surfaces. And this friction creates waste energy. And what type of energy is that? Well, think about what happens when you rub your hands together. If you rub your hands together fairly quickly, what happens to them? They get hot. And so friction of any type is a force, and it's actually being exerted over some distance. It just happens to be in the opposite direction of the motion of the object. And so it's doing negative work on a system. We don't have energy just disappearing. We're still having conversions of energy, but it's being converted to waste thermal energy that's leaving our system. And we commonly write that as delta E therm, so change in energy thermal. Or you may recall from chemistry, the symbol for heat energy is Q, as in everyone's favorite equation, the old MCAT equation, Q equals MC delta T. Right? So within a system, energy is conserved to a degree unless there are external forces such as friction, which converts mechanical energy, so normal kinetic or gravitational potential, into thermal energy or waste energy. Now, the last piece of this puzzle as it relates to energy is power. And a lot of the values, a lot of the physical quantities that we talk about in physics are rates. So changes in some value over time. Our change in energy per unit time, or the rate at which work is done, is called power. And you might have heard this in terms of cars, something called horsepower. And horsepower is a measure of the rate at which energy gets converted from basically chemical energy in the fuel into mechanical energy in the speed of the car. So the greater the horsepower, the quicker the car speeds up, because the faster we're converting chemical potential energy in the fuel into mechanical energy in the speed of the car. Now, mathematically, power is equal to work over time. Remember that work is equal to change in energy per unit time. So we can also look at power as the change in kinetic energy per unit time, or the change in potential energy per unit time. And our units for power are the watts, which the symbol for a watt is a capital W. 1 watt is equal to 1 joule per second, which is equal to 1 Newton meter per second, which, if we really want to get down to the foundation, is 1 kilogram times meter squared per seconds cubed. Have a great day. We'll see you next time.